Welcome back. This will be the Chapter 8 analysis video. And in this video, we'll talk about the paired design. And I will cover the exercises 8.4 to 8.6 on page 217 of the text. And the majority, if not all of the analyses come from this study that I'm pointing to here, Efron and Raj, 2020, Misinformation and Mortality, Encountering Fake News Headlines Makes Them Seem Less Unethical to Publish and Share. And to summarize that article, Efron and Raj asked participants to rate the ethicality on a scale of 0 to 100 of fake news headlines and compared ratings of headlines seen previously, old headlines, to headlines seen for the first time, new headlines. So what you want to do then is go to Jamovi and open the Efron Raj fake news data file. And it's this file right here that I'm pointing to with the red arrow. So you load that into the database and you can begin the analyses. So once you're in there with the data, you use ESCI, means, medians, and paired to analyze the uneth new versus the uneth old difference. Again, that's the majority of the results that we're going to see for this exercise in the book. So once you click on that, ESCI means and medians, then your dialog box comes up here, and you're going to put those two variables in the variable boxes over here on the right. So as you can see, I have the uneth old as the reference variable and the uneth new as the comparison variable. And basically what you're doing is you're subtracting the uneth old variable from the uneth new variable for this analysis. And once you get the analysis, then you will get the tables like you've probably seen before. So here's the first table. It's the results of the means and medians for those two ratings. So once again, the study authors had the same participants rate the ethicality of old fake news headlines versus new fake news headlines. And so since you have the same people doing the ratings, that's why we have what would be called a paired design. So let's take a look at the overview table here. So you have your outcome variable over here, or your dependent variable. And here's the uneth old and the uneth new. You have your mean here for the old is 66.4. There's the confidence interval for the uneth old, 62 to 71. There's the median, which is the midpoint of the data set. And then there's the standard deviation, 26.1 for that one. And then for the new, the average rating here for unethicality is 70.4. And there's the confidence interval there, 66.5 to 74.3. The median is 69.7 with a standard deviation of 23.1. So basically what you're seeing then is, on average, more recent fake news is more unethical to publish than old fake news. Okay, so you can see that right here. So the more recent or uneth new gets a higher rating of unethicality than the old fake news headlines. 70.4 versus 66.4. A difference of about 4 or so. Okay. And just to review again, there's our confidence intervals. And if you recall from the previous analysis video, you can think about those in the three different ways. One as dance of the means. Okay, so this confidence interval, we're 95% confident that this is one of the intervals that will capture the population mean. The other interpretation there would be that our point estimate, which sits right in the center typically of the interval, okay, is our best guess or best bet for the estimate of the population parameter. And it's a best bet because it's about 6 to 7 times more likely to come close to the population parameter in a random simulation analysis than the endpoints of the confidence interval. So in random simulation, the point estimate the mean of the confidence interval in that random simulation will come close to the population parameter at a ratio of about 20 versus 3 for the endpoints of the interval. And then the third way to interpret it is a prediction interval for a subsequent replication study. So we believe this interval is roughly about an 83% prediction interval. And then, so there's our two confidence intervals. And let's take a look at those just so that you should kind of practice in your mind looking at the two intervals. And when I look at those two intervals, I can see here I'm comparing the old versus new, these two 95% confidence intervals. And you can see that if I kind of manipulate this up here, if you go up here now, you can see that they overlap pretty nicely. In other words, the lower endpoint of the new, which is 66.5, is roughly in the center of the old, which goes between 62 and 70. So you can see there's, again, I'm just doing this. This is not a hypothesis test or anything. It's just so you can kind of get in the habit of sort of eyeballing it and sort of practice sort of looking, how much overlap you have between the two confidence intervals like we have in this table. The other thing you can look at with this table is the median. So if you focus down here for the median, and we talked about this last semester a little bit, if you compare the median right here to the mean over here, we have 66.4 versus 68.8. Now, if the distribution of that variable, its histogram, is perfectly normal, then the median and the mean will be identical to one another. And as you can see, for the one in the top row, the unf old, the mean is 66 and the median is about 69. So there's a little bit of a difference there, which means that the data is roughly skewed in the direction of the mean. So this would be, and again, you'd want to look at the actual distribution or histogram yourself, of course, but this is just sort of a quick check with your eyeballing that you see the difference between the mean and the median. So if I were to make a guess, I would say that when I look at the histogram for this particular variable, I'm going to guess that it's negatively skewed. Now, if you look down below, you can see that the new variable, the 70.4 versus 69.7, here we're feeling pretty good because those are pretty close to being equal. So this distribution, then, if I were to look at that histogram-wise, not knowing anything else, I would say that it's more normally distributed than the one at the top up here. Here's the next piece of output, and it talks about the correlation. So one thing with the paired measure that you don't have with the independent groups design is that the correlation between the pre and the post measures sort of comes into play in terms of the results and the analysis. And the general idea is that the more highly correlated the pre and post are, the more precise your estimate of your mean is in the population, and the narrower your confidence intervals, etc. So let's take a look at this correlation, and just to refresh, to define the correlation, which its symbol is R, okay, it's the relationship between the two variables. And the best way to do that is to look at a scatter plot, which I'm going to show you in a second. The correlation, the Pearson R correlation, ranges between a -1 through a 0 to a +1, with -1 being a perfect inverse or negative correlation, 0 being absolutely no relationship between the two variables at all, and +1 being a perfect positive correlation. Again, the endpoints here, -1 and +1, you virtually rarely see in any study, okay? Because there's always some kind of error or variability in the data that would sort of preclude you from getting that result. We get a 0.8, which is a pretty high positive correlation. So keep that in mind. That's a nice pre-test, post-test correlation. And then there's the confidence interval for the correlation. We also see the number of people in the study, and this is shown as n pairs, because remember, it's a paired design. So there's 138 people with a pre-post assessment, okay? And then the degrees of freedom in order to get the correlation and its confidence interval is going to be n pairs minus 2. 138 minus 2 is 136. Let's move on to the next one now. I think I have a picture. Oh, I guess I have that after this. I'll have a picture of the scatter plot in a couple seconds here. But before we do that, let's look at the mean difference now. So we first looked at the mean separately. Then the output gave us the correlation, pre-test, post-test, and now we're going to look at the mean difference. So the first two rows here, new and old, those are the same that we've seen before. And we've added the old subtracted from the new. So 70.4 minus 66.4 gives us the 4.06 in terms of pulling it out more decimal places, but we have a difference of about 4 there. And then there's the confidence interval over here on the right for that difference. Okay, so we have ranging somewhere between 1.41 for the difference in the population up to about 6.7. And then the last slide, I believe, before our correlation scatter plot we'll look at is the standardized mean difference, the SMD, standardized mean difference, or the effect size. One little comment here, if you've been looking in the book a little bit, the author of the textbook, if it calls a mean difference, if you just take the difference between two means and don't divide it by any kind of a standardizer to make it a standardized mean difference. If I'm not mistaken, the authors of the textbook call just a mean difference, they call that an effect size also. So, to repeat, the book is saying that if you just took the difference between two groups, the mean difference, that's it, period, they're calling that an effect size. They're also calling, when you take the difference between two means and then divide that difference by a standardizer, they're also calling that an effect size, which I find to be a little bit confusing. In my training, if it just the raw mean difference is technically, in my mind, not an effect size per se. It's just a mean difference. The authors of the textbook are calling a raw mean difference an effect size. So kind of keep keep in mind that what I'm going to prefer that you think about is that it's not an effect size until that mean difference has been divided by a standardizer. Just a little aside there for more on the confusing terminology that we have in statistics. At any rate, so here we have the standardized mean difference, which is technically an effect size. So there's our 4.06. That's the mean difference in terms of the ratings from 0 to 100 as far as the ethicality of the headlines. And then we have the SAV, and that is just the average of the two standard deviations from each group separately. The author of the textbook feels that that is the best standardizer when you want a standardized mean difference within a paired design. So for the paired design, the effect size using the average of the two standard deviations as a standardizer gives us the most accurate estimate of that effect size in the population. That's what the author is doing. If you recall in the previous chapter, chapter 7, with the independent groups design, instead of using the average, they were using the pooled standard deviation. So this gets into the importance of choosing the right denominator for the effect size. And as far as research goes, that's where most people that are doing research in this area about on these effect sizes, that's where all the controversy lies. Not in the numerator, but in the denominator. These different standardizers. That being said, I tend to agree with the authors of the textbook on this one, that if you have a paired design, just a simple pre-test, post-test design, that the average of the two standard deviations is a very good choice. And it's simple. So if we take 4.06 divided by 24.6, we get this number right here, 0.16 for the D effect size, okay, or the standardized mean difference. A mean difference that's been standardized by a standard deviation. So 0.16, if you recall from the last chapter, as far as different benchmarks, is not anything very large. It's rather on the small side. And so, for example, Jacob Cohen calls a 0.2 in psychology a relatively small effect. So we're a little under the 0.2. So we're in that kind of small range here. Right? And then there's the confidence interval for the D statistic. So you can, in your mind, you can take that 0.16 and bring it over here, and it would fit right about in the center there between the lower limit and the upper limit for our estimation of our population parameter. So this is our range here that we think are plausible for the population parameter, with the 0.16 being our best bet. And then we're talking, he includes this biased D versus the unbiased version. So there's the biased over there versus the unbiased. And again, just to refresh, the D statistic in general, as the sample sizes from which that D statistic are calculated get smaller and smaller, the actual D value does not estimate the population mean quite as accurately. That's why he's calling this one biased. Then if you apply a correction formula to this value over here on the right, you get the corrected value over here. However, in this case, you can see they're both identical. And the reason why they're identical is because the sample is fairly good size. Okay, and you only really need to worry about the biasing until you get down around 20. If you look down below here, there's a note here This standardized mean difference is D average because the standardizer used was the S average or SD average. The D average has been corrected for bias. Correction for bias can be important when the degrees of freedom, basically the sample size, is less than 50. Okay, and that's being, at 50, there still isn't much of a difference. You really need to be down around 20 is when you're going to start noticing that the correction is going to make a difference here. 50 is still the difference is pretty minor at that point, but they're calling it 50, so we'll go with that. So there's our D for our difference between new and old, and it's a relatively small effect. So then in the exercise, now we're at the scatter plot, or we're getting to the scatter plot. I keep saying that, but it's in here somewhere. I'll get to it at some point. Let's look at the figure that you can produce from the results. Okay, so there's the figure that's provided by ESCI, which is different than most software, but it's good. It's nice. So let's talk about that for a few minutes here. So you always want to look at your axes. So you can see on the y-axis, we have the unf old and unf new data, the mean and 95% confidence interval. Okay, so here's the unf old here on the left, and the unf new on the right, with the difference over here in red on the farther right. So he's going to provide, the picture shows the mean right here of the old, which is about 66, and the mean for the new, which is I thought was roughly around 70. So you can see that in the picture there. There's the confidence interval with the black bar above and below the blue dot, and then that little gray is the plausibility curve. So this is just a nice little picture that you can see. So if we look at both of those, you can see that the difference then between the new and the old is roughly over here around 4. Okay, that makes sense because from 0 to where that dotted line is about 4. Because the distance here, there's about 5 of those distances between 0 and 20. And that gives us our mean difference, its confidence interval, and also its plausibility interval, or plausibility curve, sorry. Now, the one thing that this picture provides that's very interesting is the actual data. So if you look back over here look at the blue dots, the raw data. Here's the old and the new. And what's interesting here is if you look at the little gray lines between the two, that's showing you each pair. And so you can see that even though the average goes up from old to new in terms of its being more unethical to publish, that not all of the old to new arrows or distances go up. As you can see again, not all of the old to new lines that represent each person's rating, they don't all go up. Some of them go down, some of them go up, some of them are level. And that's a nice thing to be able to see. In other words, you look at the mean here, it kind of goes up a little bit, right? But the actual raw data, which is in the center here, it's kind of messy, to tell you the truth. Or it's not as sort of perfect as you might think it would be. It's kind of messy. In fact, if you look up above up here, you can see that a lot of people just rated them the same. They're horizontal. The lines are horizontal. Some people went down a little bit. fact, there's a few people that went down over here, and then there's a few people over here who went way up. In fact, there's a person here who rated it at like 15 for old, but then if you trace their line, they brought it all the way up to like 100. Very important to have all the information. So there's our arrows showing the means and the mean difference. And then there's our scatter plot, finally. So find the correlation in the output, and here's the scatter plot of the data. Unf old on the horizontal and unf new on the vertical. So each one of these points is the combined ratings of one person. So for example, if we pick out a spot here, let's take this point right here. This is one person who rated the headline old in terms of its ethicality, rated that at a 0, about a 2 or something, right? Because it comes up to here. And then they rated the new at about, say, 28. So that's what you have. And you can see that this is a positive correlation of about 0.8, which is what we saw on the table a few slides back. Then they also ask in the exercise, how does R affect the standard deviation difference? That's the standard deviation of the each paired difference score. How does the R affect the standard deviation of the difference? Well, the higher the R, the smaller the SD difference, and the lower the R, the larger the SD difference. And then how does SD difference affect the confidence interval? Well, a smaller SD difference is going to be a shorter confidence interval, and a larger SD difference is going to give us a wider one. And knowing this will kind of get at the point of the correlation between the pre and post, so that the higher the correlation, the more precise your estimate is of the population, and it gives you narrower confidence intervals, which relates to the precision that you have. So let's move on to the last few slides here. So let's compare here. Now I've sort of added this, a little bit of extra information, but it still relates to kind of summarizing the two chapters. So let's compare the independent and paired group designs in terms of their strengths and weaknesses. So let's start out with the independent groups. The main advantage of the independent groups is that the observations or scores that you collect from the participants, they are independent of each other, so that there's no contamination of one observation by another. And so that eliminates any kind of carryover effect, for example, that you would get like you have with a pair design. So like people, like if you're giving them some kind of a paper pencil quiz or survey, both pre and post, where they're doing something like that, you're sometimes concerned about that the responses that were given on the pre somehow affect what they give you on the post, like if they remember what they said on the pre-test versus what, and then they do the post test, there's some contamination there between the pre and the post. And so with this, because they're different groups, right? It's an independent design. There's no contamination of one observation with another, which makes the statistics that you use cleaner in that sense. Now, some of the concerns of that design are, first of all, it assumes that the treatment effect is roughly the same for every participant. And as we just saw in the little diagram that the ESCI gives, the ratings are clearly not the same for every participant. Some went up, some went down, even though the average kind of says that one of them was higher than the other. When you look at people individually, you can see that they weren't the same for every participant. And that leads to the notion that with an independent design, you can't really see that effect. And that's because the two groups are different from one another. There's no connection between them. So it's difficult to quantify what's called an interaction, whereby the treatment affects different subjects differently, or i.e., different subjects rated the old versus the new fake news quite a bit differently. Some went up, some went down, some stayed the same. You can't really see that with an independent group's design like you can with a paired. So that's a potential concern. Another concern is that you must estimate mu, your population parameters, for two separate groups. And anytime you have more than one group, that'll increase the standard error or the sampling error, and it lowers the power and the precision of your estimates and your statistics. Also, unlike the paired design, you must also contend with the sampling error that's related to estimating the difference between two separate groups. That is, the estimated treatment effect, the mean difference, is kind of confounded by the additional sampling error that comes with estimating the difference between those separate groups. So there's more error in the independent design. That's one thing to kind of keep in mind. Let's look at the paired groups design. Some advantages and disadvantages for those. First of all, an advantage is that the comparison is within each participant. So, like we saw on that graph, you can get an idea exactly how each participant is responding, sort of pre to post, for example, because you have the same people doing that. So when the pre and post measures are reasonably correlated with one another, that mean difference can be estimated with good precision. And because there's only one group there and not two, we have less sampling error. And the other thing is you need fewer participants then, because you only have one group doing both ratings. So the idea would be, all else being equal, you would need half the number of participants for a paired design as you would for an independent design. A couple of the concerns, one is that there's those carryover effects, which are the pre-test affects the post-test response due to memory, learning, etc. So you have to kind of think about that as you're designing a study that is a paired design. The other is confounding, and that is, for example, it's a confounding is where there's sort of an unwanted influence on the responses that you're obtaining in your study. So, for example, here, One would be, for example, subject fatigue because the treatment is too long. So if you have a paired design where the subjects are going through a fairly long treatment period where they're doing something or learning something, etc. If that's too long, some of the subjects could get, sort of tired, and that will influence maybe how well they do on the post test, for example. So you have to be a little bit aware of those kinds of things too. That would be considered a confound. Now, unlike the independent design, like I mentioned, the paired design does allow you to detect and report an interaction effect. And that's also a advantage in a way for the paired design because the interaction. So what I mean by that is that um, it's a consistent a consistent situation where the certain subjects are responding in one way and other subjects are responding in a different way that shows up as like a pattern that you can detect. And that's something to know because you can't see that if you just look at the mean difference. If you just look from pre to post, you look at the mean on post and the mean on the pre, you just see the two means. That's it. And even though they may be different, there may be something underneath that that's creating that you want to know about. Okay? And so let's talk about that. I have one slide on that to show you what you can see with this paired design that you kind of can't with an independent design. And that's this right here. This is the paired design, what will be called main effects and interaction effects. So first thing, just focus over here, little diagram. So I made up some data. I have 6 subjects, pre and post, some kind of a rating on something. So we have the first subject there. They at pre they rated or scored a 2, and on post they got a 6 for a change of +4. This subject started out as a 2 and they went to an 8. I'm sorry, they started out as a 4. My eyeballs are in the wrong spot. Started out as a 4 and went to an 8, so they have a change of 4, etc. So you can see the pattern here: 6 to 10, 8 to 12, 10 to 14, 12 to 16. So the mean for the change, the mean is 4, obviously, and the standard deviation is 0. There's no variability in this data right here because they're all the same. And if you graph that, you get what you see right here. Pre, post. Everybody went up exactly the same. You'll never see this in real life, but this would be what would be called a pure main effect. There's no interaction here. Everyone's responding the same in a sense in terms of the difference. They're starting out at different levels, but whatever it is that they're rating or whatever the treatment is in between, it's each person is going up by 4 points on whatever the thing is that you're doing. So this is clearly what you would call a main effect. All the subjects increased 4 points pre to post. However, look over here now on the right-hand side. Same number of subjects, but they respond in different ways. So let's take a look. The same pretest scores, but the first 3 subjects went down 4 rating points at post, and the last 3 subjects went up 4 rating points at post. The mean here is 0, okay? And so if you just look at the change without looking at this more carefully, you might think that the treatment had no effect because the mean is 0 pre to post. Standard deviation 4.38. And here's what the graph looks like over here. Again, looking at the mean, you would conclude that nothing happened. But you can clearly see that there's something happening here. 3 of them went up, 3 of them went down. So this is a clear pattern of where the treatment that occurred between pre and post is affecting different subjects differently. Very important. Now, you don't know exactly why this is occurring, but you can at least see it happening, and you're able to report that with this type of a study design. And this would be called an interaction effect. The treatment had different effects on different subjects. Half decreased 4 points and half increased 4 points pre to post. And so this is the thing that you're able to kind of see with a pair design that's much more difficult to kind of see with an independent design. There's another thing you can do. There's an index that you can compute using the standard deviation of the change scores. So if you look right here, over here on the left again, where I have the arrow, you can see that the standard deviation here is 0, giving us this pure main effect type of a pattern there. And you can see over here we have a standard deviation of like 4.38. So there's an index that you can compute that relies on the change score standard deviation, the pre-test standard deviation. It also incorporates the reliability of the measure and the size of the study, the n size, and you can compute this thing. And it crosses over from a negative to a positive. So I computed that. I'm not going to go into too much detail on that, but it just gets to the fact that with this main effect design, with the pair design, you can get a little better handle on the interaction and you can quantify it. So the one on the left over here for the main effect, I calculated this interaction index, which is just a little bit of an extra information not in the book. I get a minus 1.87, but when I do it over here for this one over here, I get 4.54. So as the index gets more positive, there's more likely to be an interaction that's going on that you would want to look at and talk about in your results. Okay. And then I have 2 more slides. We have, if you combine these two, so a potentially better strategy is to have participants randomly assigned to separate control and experimental conditions. So you have this physical control group there. Both groups complete the pre-test and post-test, but the control group does not receive the treatment, or they might complete a comparison task instead. And the control condition acts as a standard of comparison to the treatment. Okay, this is a potentially better strategy, and this design incorporates elements of both the independent and paired methods. And so that would look something like this here. So you have your participants here, and you randomly assign them to the upper group here, which would be the treatment group, pre-test, treatment, post-test, or they would be assigned to the pre-test, no treatment, post-test, the control track, if you will. And so what we have is for each group is a within, each group is a paired, but then between the groups you have an independent design. So this is a combination of a paired situation when you look at each group individually, but if you look between the groups for analyses, you have an independent situation because you have different people in each condition. Okay, so it's just to throw that out there. I think the author talks about that a little bit in the textbook too. And then the last slide then is, so if as a general rule, there's nothing hard and fast here, but You can prefer the paired design if it's practical and you believe that carryover and confounding will be minimal or can be minimized. Okay, because you just need fewer subjects. You can get a more precise estimate. You can have more power and precision. You can also look a little more at interaction effects. The bottom line then is consider the pros and cons of each design for your research context, at least when we're talking about these two types of designs. But importantly, always design the study, whatever it is, around your research question or hypothesis. Don't try to tweak your research question or hypothesis to fit the study design. That's a no-no. So very important there on that last one to kind of keep that in mind in terms of the future when you try to design your own research for your doctoral degree. That takes care of that one. And so we'll have the quiz up for that. And if you have any questions, please send me an email. Thanks for watching.